Hello, class. Welcome back to lecture 18. Today we are talking about the Dirac delta function. Very fancy sounding thing, and it's very cool, and the Laplace transform is good for dealing with it. And let's get to it. Okay. Oops, there we go. So next, we try to model an interesting situation that comes up a lot. Situations where there is a big external force acting on something for a very short amount of time, very quickly. And then it stops. So for example, when you just have like a ball on the floor and it's just sitting there, and then you just kick it very hard for like one fraction of a second, then that's this type of situation, right? So there's no force on the ball and you just kick it really hard for one tiny second and then the force is not acting out anymore. Stuff like that. And then we can combine this idea with what we've done before, like springs and stuff. So let's say somebody comes up to you and says, oh, Laplace transforms, they're not that cool. Obviously, you're going to get mad. So what do? You grab them and you pick them up and you attach them to a spring because you know how springs work now. And so you attach him to a spring. And so he's bouncing there like before, but now what's different this time is you can also do a really strong external force for like one quick second. So they're already bouncing. And then while they're bouncing, you hit them with like a hammer or something really hard. And then it's just like one giant external force that enters the system very quickly, and then it's not there anymore. But then obviously the bad guy will continue to bounce up and down, but now like harder because you just hit him with the hammer. So stuff like this. You can also apply the same idea to like circuits, but we haven't dealt with circuits much, but the same idea can happen. So maybe you just have a circuit just having fun on its own. It's got a battery providing voltage that's going through and creating a current. And we did some examples like that a long time ago, but now instead of an external force, you'd have like this giant, maybe like a lightning bolt hits the circuit or something. So you have this giant extra voltage that just happens instantaneously and then it's gone again. Maybe your circuit has angered Zeus, so he shoots lightning at it or something. So things like this are what we're trying to model. So this is where the Dirac delta function enters. Okay, the title of the lecture today. So it's not actually a function, so I don't know why everyone calls it a function. I guess it's something called a generalized function, which we're not going to learn. But we're just going to sort of pretend it's a function and try to deal with that. So it's not actually a function in the usual sense. And so instead of defining it formally, so you can formally define it, which is a bit tougher to do. Instead of doing that, we'll just list some properties that are good about it. Okay, so here are the properties. Here, it's getting too long. Okay, so the idea behind this not really a function is that most of the time it's 0. So like the idea is like nothing is happening. So it's mostly just 0. It's called delta. I should have named that earlier. So the name of the function is delta, and then you put whatever in here. So it's a lowercase delta, Greek letter. In any case, so the idea is that it's mostly 0 because nothing's happening. So it's 0 when time is not a. So the idea is a is this time where something happens suddenly, very quickly, some big giant force comes in at time a. So when you're not at time a, nothing happens. That's what this is saying. But then at time a, so I guess it would be this, the idea is that it's like this infinitely big force. So it's just a giant force. So this is not a technically well-defined property here that I've written. This is just the idea. So the idea is it looks something like this. 0, 0, 0, nothing's happening, and then whoop, giant infinitely high point at A. Something like that. So then the reason why you don't just make it a really big number as opposed to infinity is because we want this third property to happen, which is the most important property, which is if you integrate around it, so I guess I'll go from C to D, around this very nice point A. So what does the integral normally do? It tells you like the area under the curve, right? So normally, if you had a graph that was just a point, something like this, just one single point, well, the area under a point is 0. So if you integrate around this point from C to D, you would just get 0 because there's no area under a single point. But because we've made the magnitude of this force be infinite, the idea is now there is an area underneath this point, and it's just 1. So this is like the unit Dirac delta function. So the idea is if I find the area around this, as long as I have the point in the interval, then the area will be 1. So this is specifically when the time A is between your two numbers, C and D. Okay, so if you integrate around this infinitely high point, then you get an area of 1. Very strange function, not a function. And then this last property will just help us do the Laplace transform. So we're not going to try to prove these properties, but we're going to use them. So if you integrate a function times the Dirac delta function around that point, it just becomes f of that t value a. Okay, so we're going to use these properties to immediately conclude. Actually, it's just number 4 that does this for us. But the Laplace transform of the Dirac delta function is what we're really after, and now I can do it using number 4. The idea is I can just make d go to infinity and make c be 0, and this property will still hold. So the Laplace transform by definition is this. But then according to this property number 4 that we've provided here, it's the Dirac delta function times a function of time. So when I integrate it from 0 to infinity, I'm just going to plug in a for t. That's what's happening here. So this is just going to be e to the negative sa. Or more often going to write the a in the front. So like that. Okay, so this is all we need to work with the Dirac delta function. Now we're going to model some situations. Okay, see how it goes. And then we'll see how the intuition matches what we actually get. All right, so let's do a spring problem. Let's just simplify it a bunch. The mass I'll just give you is 1 attached to a spring. Whoops, yeah, sorry, a mass. A mass with mass 1 is attached to a spring with spring constant K equals 1 also. And let's pretend there's no air resistance. And after some amount of time, so 2 pi seconds, you hit the mass with a hammer. So you just hit it really hard. And so this will be modeled by, we're going to do 4 Dirac delta t minus 2 pi because it's happening after 2 pi seconds. So that's the time at which the hammer hits. So it's t minus that number. And then the 4 is just saying we're just multiplying it by a number to make it bigger than normal. It would just be a 1 otherwise, but now we want a 4. Okay, and then we're also going to suppose that it was already moving. So it's already set in motion with no initial velocity, but by releasing it 1 meter below equilibrium. Okay, so here's the problem. So we got this spring, got this mass, and it's already been set in motion by pulling it down a little bit, 1 meter. So it's already bouncing up and down. And then after a certain amount of time, you come and you bop it with a hammer. And the force that you hit it with is modeled by the Dirac delta function. Okay, so what's the differential equation? Well, it's still a spring problem. So it's still this thing. And we have initial conditions which set it in motion. So in this case, we have P of 0 equals 1 because I release it 1 meter below and I don't give it any initial velocity. So this is 0. But now the external force is nothing. There's no external force besides this Dirac delta function. So we're going to stick that there. Okay, so then what do we get as our differential equation modeling the situation? Well, there's no air resistance. K and M are both 1, just to simplify things. Now I have this Dirac delta function as my external force. Okay, so we're going to use Laplace transforms. We're going to do it on both sides. And away we go. So remember that the Laplace transform of the second derivative is s squared times the Laplace transform of the function that you're looking for minus s times the function at 0 minus the derivative at 0. And then there's no first derivative to worry about. So we just jump to there. And then on the right side, I could take out that 4. And we just learned that the Laplace transform of the Dirac delta function is e to the negative however much you shift the special time that you hit the thing with the hammer at, that number times S. Okay, so now we got to solve for L of P. So let's see, S squared minus S, because P of 0 is 1, minus 0 because P prime of 0 is 0. 4e to the negative 2 pi S. And so I get the L of P things together by factoring it out. So I get S squared plus 1. I got to add that S over to the other side. Oops. And then I got to solve for L of P by dividing. And it's always good to write it in suggestive ways so that it's easier to deal with. Okay, so now we do the inverse Laplace transform to figure out P, what we're really looking for, the position of the mass. And then we use our table to figure these out. Sometimes we have to rewrite them, that's okay. Okay, so here in the first part, we just take out that 4, and then we remember that if you see an e to the negative something s, then when you inverse Laplace transform, that is going to turn into a unit step function shifted by that amount times some function that you need to figure out where you plug in t minus 2 pi. And that function that you need to figure out is the one whose inverse Laplace transform is this leftover bit here. Okay, and then on the, so we'll figure that out in a second, but first on the right side, so S over S squared plus 1, that one is just in a table, that's just cosine of t. So that's what this is becoming. Okay, so now I very quickly have to figure out this extra bit, g of t. So that's also just in a table. So what's g of t? I think that's just sine of t. If you look that up, 1 over s squared plus 1 becomes sine of t. But now I'm plugging in t minus pi over 2 into it. Sorry, t minus 2 pi into it, so it becomes that. Okay, and then that's it. So that's the position function of the spring. And so what's it saying? So it's basically saying like, all right, here's 2 pi. Until you get to 2 pi, it's just cosine. So it's just having fun being cosine. And then all of a sudden you hit it with a hammer and it adds this extra amount. And so if you go and graph it, it's just going to bump it up like that. And then it's going to continue oscillating at that amount instead. It's not going to be quite, it's going to be like a little bit above 4 if you go and actually graph it. But that's the idea, is at this special time 2 pi, that's when you hit it with the hammer. So that's when all of a sudden it changes what it was doing. Okay, so let's just keep playing around with this example and changing little things one at a time, just to see what happens. So this time, let's suppose there already was an external force. Before you hit it with the hammer. So I'll just do a nice simple one. How about sine of t? So it was already being shaken up and down by this external force of sine of t. And then after 2 pi, you did the same thing. And we're still going to have the same initial conditions as before. Okay, so we don't want to change too much at a time. All right, so there's still no air resistance. So what do we get? We get P double prime plus P equals sine of T is our external force plus this extra amount after 2 pi time. Okay, so works the same way. We Laplace transform everything. So I'm gonna skip a few steps. Okay, there's that. Laplace transform that. So now the Laplace transform of sine is 1 over s squared plus 1. The Laplace transform of this thing, we already did that last time. It's the same. Okay, so it's going to be a little bit different. Still going to factor out my s squared plus 1 here, and I'm going to add the s over. And then divide to get the Laplace transform of p alone. And then we are on our way. Okay, s squared plus 1. Dividing by this one, it's going to make 2 of them, so that's going to be squared. 4e to the negative 2 pi s times 1 of them here, plus s over s squared plus 1. Okay, so this first term is the most interesting term. Let's see, where does it come up in our table? So we got to check our table, because this is slightly different than what we're used to. So what we're going to do is we're going to use this one. The inverse Laplace transform of 2 over 2a cubed over s squared plus a squared squared. That's the one we're going to look at. And so we can see it's the same, except there's no 2 there, and a is 1. So all I have to do is multiply this guy by a 2 over 2, and then I can use it. All right. So now it is, oh, I didn't say what this actually equals. Okay, so the formula for this one is sine of AT minus AT cosine of AT. If you look in the table. Okay, so I've had to take out a 1/2 to put this 2 in there. And now a is 1. So this is going to be sine of 1t minus 1t cosine of 1t. Okay, so that's not so bad. You just look it up in the table. You have to be a little bit clever to see that 2 just needs to be multiplied there and divided. Okay, and then the rest of them I think are the same. So this is, oh wait, so now we're already inversing. So this is p now. Okay, and then the next one we did in the previous problem, this is just for a step function shifted over 2 pi times, and then g of t minus 2 pi, but g of t is whatever the inverse Laplace transform of this guy is, which is sine of t. And then the last one is, that's just cosine of t when I inverse everything. Okay, so then just about done. So I guess I'll distribute the sine through. I mean, the 1/2 through. And then I will plug in t minus 2 pi into sine. And that's it. Okay, so this is the function. So let's see, don't want to say anything else about this one. So you can go graph this one too. And it's interesting. I'm sure I didn't graph this one ahead of time, so I don't want to guess randomly. One thing I do want to say is I've been avoiding this, but But if you remember properties of sine and cosine, and the fact that they're periodic with period 2 pi, if you wanted to, you could rewrite this just as sine of t, because sine shifted by 2 pi is the same as sine. But I just haven't been doing that. Could have done that previously too. Won't change it at all. Okay, so that's that one. I think I just want to do one more today. So hopefully this video is a bit shorter than the last one. That's why I felt bad about the last one, so I made this one shorter. Okay, so now let's do air resistance. AKA just any old damping. So we're just going to say B is 2. And then let's change the external force. Instead of being sine, let's just make it 3t. And then let's change the hammer to be a little bit stronger. So we're going to do 5, but it's still going to be at 2 pi. Okay, so I'll just see if that 5 does anything really. All right, so now the differential equation, now I have air resistance. So, and the external force is 3t. So what's really going to change is it's just going to get more complicated, but it's still going to be everything like the same. So I'm not changing the initial conditions either. So let's do that too. Okay, so now when I Laplace transform, this first stuff will be exactly the same. So that's all the Laplace transform of this thing. But now I also have this other term who I'm Laplace transforming. So it becomes 2 times s, the Laplace transform of p, minus p of 0. That's what the Laplace transform of p prime is. And then the Laplace transform of p is just the last term. Okay, so then on the right side, Laplace transform of t is 1 over s squared. And the Dirac delta just becomes e to the negative, still 2 pi s. So that's all the same on that side, basically. Okay, so now there's a 5 instead of a 4. All right, so now we have to simplify. So p of 0 is 1, p prime of 0 is 0. Distribute this 2 through. P of 0 is 1, so that just becomes 2. Great. So now we get LP alone by factoring it out of s squared plus 2s plus 1. And I have to add this s and this 2 to the right side. And then finally, I can get L of P alone by dividing. So one thing I'm going to immediately do is realize I can factor this as s plus 1 squared. So it's s plus 1 times s plus 1. So then when I divide it, I'm just going to write it like that. And you got to be a little bit careful here. So what can we do? Well, actually, I guess I'll keep this 3. Oh, what is this stupid? Okay. I'll keep this 3 up here because I'm going to do partial fractions on that. So I might as well just keep 3. So here, this thing I'm going to do partial fractions. So I'm just going to plug that in to some partial fraction decompositionizer for me, so I don't have to deal with it. And this will become 3 times 1 over s squared plus 6 times 1 over s plus 1 plus 3 times 1 over s plus 1 squared minus 6 times 1 over s. So that's all this stuff. Okay, so the trouble is, like, when you do partial fractions and you have squared terms, you have to remember this trick where you have both the term and the squared term. And so you're gonna have 4 terms here if you actually do it manually. Okay, so that's that. This, I'm not gonna deal with yet. And this, I'm gonna partial fraction as well. So we can plug this one in and it will end up as, let me see. Oh, this one's not so bad. It'll end up as 1 over s plus 1 plus 1 over s plus 1 squared. Okay, so you partial fraction that as well. All right, so we got a lot of stuff here, but now it's all in good forms that you can find the inverse Laplace transform of. So let's do it. Okay, so I don't want to rewrite all this stuff, but we're inverse Laplace transforming now. All right, so let's just take it one step at a time. So 3 times 1 over s squared, that just becomes 3 times, and then the inverse transform of 1 over s squared is just t. This is an exponential form. So if you have 1 over s minus a, it becomes e to the negative a. So in this case, our a is negative 1. So it becomes 6e to the negative t. Maybe I'll draw little arrows so you can see where everything's coming from. Okay, this next one is new. So the next one, let's highlight it with a different color because it's definitely one that we haven't seen before. So let me go off to the side and use this other table. So the one we're using now is that the Laplace transform of t to the a e to the negative st is a factorial over s plus a to the, hold on. Oh no, let me think. I have incorrect letters here. This is I'm getting tripped up, sorry. Okay, sorry, this should be a. And this should be n. Okay, I hope this is the right form. Otherwise, look at the table. In any case, I know it's correct for what I'm using it for, luckily, because I wrote that down. I should have written the general form down. But what we're using it is for t to the 1, e to the negative 1t. So the Laplace transform of this is going to be 1 factorial over s plus 1 squared. And this is what we have in a couple of places, 1 over s plus 1 squared. So we identify that we see a 1 over s plus 1 squared in a few places. So right now we see it here. And then we go and look at the Laplace transform table and we see that, okay, it must have come from this then. All right, so then we get t e to the negative t. So this is correct. I'm just worried I wrote down the general formula incorrectly, but this is correct for this particular case. Okay, so continuing on. So this thing is a standard one that we've seen a bunch of times. That's just 1 over s becomes 1 when you inverse. The next one is a unit step unit step function because of the e to the negative 2 pi s. So I got to figure out what g of t is, but remember, it's just the inverse Laplace transform of whatever is next to the e, and that's just the same thing as we saw here. So what's going on is that g of t is the same function, t e to the negative t, because that's the inverse Laplace transform of 1 over s plus 1 squared. Okay, so that's what g of t will be once we get to the next step. Let me switch colors now because there's too much the same. All right, so this guy is another exponential e to the negative t. And here we see our 1 over s plus 1 squared again, t e to the negative t. The same thing we just did. All right, so we're just about done. We just got to simplify a little bit. So 3t plus, so notice I have an e to the negative t and a 6e to the negative t, so that's going to be 7 of them. And I have a 1t e to the negative t and a 4t e to the negative t, so that's going to be 4 of those. Oops. And then I got this 6 here. I guess I'll just keep it there. And then finally the step function part. So now I know it's this t business, e to the negative t is, and so that's what I'm replacing my 2 pi with. Okay, so that's it. That'll be the function. Okay, so that's it for this time. Next time we will do some more applications of Laplace transforms. We'll do systems of equations, so we'll see how they help there. Okay, see you next time.